to OWOS. This is the second talk of the third season of the optimization online seminar. So it is my great pleasure to introduce our speaker today, who is Monique Laurent from CWI Amsterdam, which is the National Institute for Mathematics and Computer Science in Netherlands. She is also affiliated with Tilburg in Netherlands, and is a great researcher in discrete mathematics optimization with very important contributions in polynomial optimization, STP programming. So in the last two seasons, there were not so many talks from this area of mathematics on optimization, so discrete optimization. So it's great to have Monique as representing this area. So Monique, thank you for accepting our invitation. The floor is yours.
Okay, thanks a lot. So let me try to go back to share screen. So, okay. So thanks a lot, Radu, and the organizers of the seminar. Thanks for the invitation. It's a great pleasure for me to give this lecture. So if there is anything not going okay, you tell me, I guess.
Yes.
But so far, so good.
Yes,
so,
perfect.
What I want to discuss today is actually not so much discrete optimization, but more polynomial optimization. And the focus will be on the analysis, so on the performance analysis of some sums of squares hierarchies for polynomial optimization. And this is based on several joint works together with my colleague at Tilburg, Etienne de Klerk, and Lucas Slot, who is now doing his PhD at CWI. So let me get started. So what do we look at? We look at the problem of minimizing a polynomial f over a feasible region K, which is assumed to be compact and most of the time semi-algebraic. So which means defined by polynomial inequalities. So this is what polynomial optimization is about. So one wants to find the global optimum, which I denote by f min of f over the set K. So of course, this is a very general problem which falls within nonlinear, non-convex optimization. And of course, there is an enormous literature on that, but the focus today will be on so-called polynomial optimization methods, which exploits algebraic structure which is present in polynomials to devise hierarchies of bounds based on sums of squares of polynomials. So this is a general problem which captures many NP-hard problems, and I just mentioned one, the combinatorial problem, which asks to compute the maximum size of a stable set in a graph. I mention this because there are several equivalent reformulations for this problem, which say that you can reformulate it as optimizing a degree 2 polynomial over the cube or the simplex, or optimizing a degree 3 polynomial over the sphere. And I just show you these reformulations. So on the left, we have maximizing a quadratic function over the hypercube gives alpha, or minimizing a quadratic polynomial over the standard simplex delta n gives you 1 over alpha. So this is due to Motzkin, this is a famous Motzkin-Strauss formulation. Or there is this other reformulation due to Nesterov, which says how to find alpha via maximizing a degree 3 polynomial. So as these examples show, optimizing a degree 2 or degree 3 polynomial over very simple sets such as a cube or simplex or the sphere are already NP-hard problem. So the lens we are using is the lens of polynomial optimization, and which enables to define hierarchies of bounds. So there are two main hierarchies I want to discuss. First, a hierarchy of lower bounds, which are used by Lasserre and Parillo, which are based on sums of squares representations for positive polynomials. So this gives bounds which I denote by FR, where the R is as a subscript to denote a lower bound. And there is a hierarchy of upper bounds, which is now known as measure-based upper bounds due to Lasserre, which gives bounds which I denote by FR, where the R is a superscript to indicate that it's an upper bound on F. I will define this in a minute. Common feature of these bounds is that if you fix R, you can compute the bound using semi-definite programming. And the reason being that sums of squares of polynomials can be modeled via semi-definite programming. So for fixed R, we get a semi-definite program roughly involving a matrix of size n to the R, so which can be done efficiently for fixed R, at least in theory. And the second common feature is that the bounds converge asymptotically to the minimum of F over the set K. So in this lecture today, the main focus will be on the error analysis, how good the bounds are in terms of the degree bound R. And I will focus mainly on the upper bounds, but nevertheless, let me start with briefly recalling a few facts about the lower bounds, which are probably what is more known to the community here. So I want to start with introducing what is now known as the Lasserre-Parellot sums of squares lower bounds. So to define them, the idea is very simple. We start from the problem. We want to find F min, which is a minimum of F over K. And of course, this is the same thing as finding the largest scalar lambda for which a polynomial F minus lambda is non-negative over the set K. And then the idea is that when K is semi-algebraic, which means that it's defined by a bunch of polynomial inequalities, so here the Gj are polynomials, then one can replace the hard non-negativity condition, which asks F minus lambda non-negative over K. This is hard, but one can replace it by an easier condition, namely, we try to reformulate the polynomial F minus lambda as a weighted sum of sums of squares. And this means, to be more concrete, we try to reformulate the polynomial F minus lambda as S0 plus S1G1 plus SMGM. So weighted combinations of the constraints where the coefficients S0, S1, Sm are sums of squares of polynomials. And we put a degree constraint, a degree bound on the summand. So we say that every summand should have degree at most 2R. And in this way, if we search for the largest lambda for which F minus lambda has such a decomposition, we get a parameter F sub R, which can be computed using semi-definite programming. So by construction, we get a lower bound on the minimum. If we let the degree R grow, we get a better and better bounds. And the bounds converge asymptotically to the minimum of F. And this convergence results follows from a result in algebraic geometry from a Putinar, which says that if you have a positive polynomial on the set K, then it admits such a decomposition. And as already said, we can compute each bound using semi-definite programming. So this is in a one slide, the Lasserre hierarchy of lower bounds. So as announced, I am interested in understanding what can we say about the error. So if we look at the relaxation of order R, how good is the bound at the order R? So how far is the bound FR from the minimum? So there is a very general result of Nie and Schweighofer, which applies to general semi-algebraic compact sets. What they show is that there is some constant C for which we can upper bound this error by this quantity here. So there is a constant, we don't need to look at it, depends on the degree, on n, on the polynomial. But let's look at the dependence in R. So R is the degree bound on the sum of square degree. So the dependence is rather weak. So we see that we have the logarithm of R, and then on top of that, we take a root of the logarithm of R, and the base of the root is this C, which is a constant C, which depends on set K, and which is not known explicitly in general. And on top of that, this estimate is valid only for very large R. But this is a very general result, which gives this permits to get again the asymptotic convergence, but this doesn't give this gives a weak estimate which doesn't match the good practical performance of the bounds. So researchers have been, one is interested to understand, can we get a better analysis for special sets? And a recent result of Fang and Fuzzy shows that indeed for the case of the unit sphere, then one can show an error analysis in 1/r², so quadratic in 1/r. And this improves an earlier result in 1/r, which was obtained using techniques from quantum information from Doherty and Wehner. But so there is not so much known. This is a current area of research to try to improve this analysis for other sets K, and I will come back to this towards the end of the lecture. But for now, I want to move to the upper bounds. And what can we do about the error analysis of the upper bounds? Because actually it turns out that the error analysis for the upper bounds also plays a role for analyzing the lower bounds. So from now on, and for the rest of the lecture, I will move on to the upper bounds. So let me first introduce the upper bounds, which are also known as the measure-based upper bounds, which can be defined as follows. So we start again from our original problem, which is to find the minimum of f over k. And it's very easy to see that we can reformulate it as finding a probability measure nu on k and minimizing the expected value of f. So this is very easy. It just comes by identifying points x with Dirac measures on k. And then you take convex combination of Dirac measures and you end up with probability measures on k. So this is reformulating our problem as a optimization problem over measures. And what Lasserre showed is that when k is compact, actually we do not need to optimize over all measures nu. What we can do is let us fix a measure mu, which I will use a color blue for this fixed measure. We fix a measure mu supported by k, and then we restrict the search to probability measures nu which have a density with respect to mu. And this density h actually can be restricted to be a sum of squares of polynomial. So in other words, the minimum of f is equal to this program, to the minimum of this program, where the minimizing variable is h, is assumed to be a sum of squares, and to give a density function, a probability density. So integral of h d mu should be equal to 1. And if you want to get something which we can compute, so what we do, we simply add a degree constraint on the sum of squares on which we're optimizing. We say we pick an integer r, and we say that we restrict the degree to be 2r at most. And in this way, we get the parameter fr, where r is now as a superscript to indicate that this is an upper bound on the minimum of f. So by construction, we get upper bounds. If we let the degree bound r grow, then we get a bound which is closer and closer to the minimum. And by construction, the bounds converge to the minimum of f. And if we fix r, we can compute the parameter fr using semi-definite programming. And actually, it's a very simple semi-definite program because it has only one linear constraint. So this will turn out to be just actually an eigenvalue computation. But I will come to this in a few minutes. So there is a small but which I should stress, is that if we want to compute this parameter, we actually need to know the moments of the measure. Because to compute, for instance, the expected value of f, we are going to need the moments m alpha of the measure. So that's a restriction of this definition. On the other hand, as we already mentioned, working optimization problem over simple sets like the cube, the ball, the simplex, or the sphere are already carrying very hard problems. And we can, for instance, select the Lebesgue measure on these sets, and then the moments are known explicitly. So at least for such sets, it makes sense to look at this hierarchy of bounds. So just an example, maybe to fix ideas, here is a polynomial known as the Motzkin polynomial. If we want to minimize it over the box, it has 4 global minimizers, which we see here at the 4 corners of the cube, of the plus minus 1 cube. So let us see how the optimal sum of square density would look like. So at degree 12, it looks like this. So we see that it's high values on the border of the plus minus 1 cube. And if we increase the degree, so we see that the optimal sum of square density gets peaks which are located at the 4 global minimizers of the function. And as the degree increase, the peaks are getting higher and higher. Degree 24, the peaks are getting higher and higher. So what this picture suggests is that this optimal sum of square density is trying to look like a combination of the Dirac measures at the 4 global minimizers. So this upper bound is searching for an optimal sum of square density, which looks as close as possible as a combination of Dirac measures at the global minimizers. And the objective is to understand how does the error range behave as the degree grows. So the error range is the difference between the upper bound FR and the minimum of F. So this error range now, of course, it depends on the set K, where we minimize the polynomial F, but it also depends on the measure which we select as reference measure on the set K. And this freedom of the measure, actually, we will need it throughout the analysis to be able to understand various sets K. So in this table, I'll show you an overview of what is known. And after that, we will go into what are the techniques to show such results. So in this column, I show the reference measure, which we pick. And here is the set K. So the first results are for the hypercube. This is the starting point. And actually, the most simple hypercube is just the interval in dimension 1. So this is somehow the baby case, but which is fundamental to derive many of the other results. So for the hypercube, the sphere, the ball, and up to here, we see that we can show an error analysis in 1 over r square. And here, for the hypercube, for instance, it depends. So for linear polynomial, we get it for an arbitrary Jacobi measure, for any lambda at least bigger than -1. If we want to do an arbitrary polynomial at first stage, we can do it only for the Chebyshev measure when lambda is -0.5. And then by doing some other tricks, we can extend this to any lambda at least -0.5. Using the analysis on the hypercube or on the interval, actually, we will be able to deal with the case of the sphere. From that, we will be able to deal with also with the ball, and then the case of the simplex and any round convex body. Round meaning that you have inscribed and circumscribed tangent balls at any boundary point. So a nice looking convex body equipped with a Lebesgue measure. And finally, if we want to be able to go to much more general sets, so like arbitrary semi-algebraic set being fat, meaning that the dense, having a dense interior, or general convex bodies equipped with the Lebesgue measures, and we can do it, but we have we will need a different trick, and we will have this additional log r square coming into the error analysis. So this is an overview of the results, and now I want to tell you what kind of mathematical tools we use to derive these results. So there will be, let me start. So what are the key tricks or the key strategies which we use for the proof? So a first key strategy will be to reformulate the parameter as an eigenvalue problem, and then to relate it to extremal roots of orthogonal polynomials. And this will be the key to understand the behavior on the interval -1, 1, equipped with the Chebyshev measure when we have an arbitrary polynomial. And for the case of linear polynomial, for an arbitrary weight function on the interval -1, 1. So this will be the first key fact. which then combined with a number of tricks like taking Taylor approximation, integrating local similarity, we will be able to transport this result, 1 over R squared, to other sets and other measures. So we'll lift the results to such sets which are shown here. If we want to go to more general sets K, so arbitrary convex bodies or arbitrary semi-algebraic sets, so we will be able to show this rate, which is a little less good than the 1 over R squared, but we will need more different tools. Namely, roughly speaking, we will go back to the univariate case using push-up measures and by designing nice sum of square densities using needle polynomials. So these 3 blocks somehow kind of illustrate the rest of the lecture now. So let's go through it. So first, a very basic and easy trick which enables us to reduce the analysis for general polynomials to the analysis of quadratic polynomials. And that's very easy. It's simply to realize that if we want to minimize f, an arbitrary polynomial over k, so say A is the global minimizer, then we can upper estimate f by taking the Taylor approximation at degree 2. So let's call it G, which is written here in red. So this G has several properties. It's quadratic, it's separable, and it has the same minimum as f over k. So based on this, the error of f is upper bounded by the error of G. So it's enough to analyze quadratic and separable polynomials. And that's what we will use. We restrict ourselves to quadratic polynomials. And sometimes we will even have linear upper estimators, which will make our life even easier. So that's a basic trick. It's enough to analyze quadratic polynomials. So we want to analyze the case, as I mentioned, the case of the intervals, univariate case plays a crucial role. So, and we will do this by using an eigenvalue reformulation of the bound. So let's start with this. So this eigenvalue reformulation is valid always, not only in the univariate case, it's valid always. So let me mention this here. So here I just recall the bound, the definition of the bound. And the next step is, instead of expressing polynomials in the monomial base, let us express them in the orthonormal basis, which is formed by the polynomials P alpha, which are orthonormal with respect to the reference measure mu, which we have selected. Remember, we have K, we fix a measure mu on K, and now let's take the orthonormal as basis. We pick the basis of polynomials which are orthonormal with respect to the scalar in a product given by this measure mu. And let us define this matrix MR of F, whose entries are, you integrate F P alpha P beta over K. So it's a moment or Hankel type matrix. It's indexed by all the monomials up to degree R. So it's indexed by this P alpha P beta. And now a polynomial H is a sum of squares of polynomials if and only if, this is not difficult to see, if and only if so exists a matrix X, positive semi-definite, for which you have this identity, where here we put here the vector of polynomials P alpha and here the transpose. And it's just a reformulation, then we can rewrite the expected value of FH. This is nothing but the inner product of this moment matrix MRF taken with this matrix variable X. Then we have these constraints here, which says that the integral of H should be equal to 1, and the integral of H actually is nothing but the trace of X. So we can reformulate the bound FR as minimizing this objective function subject to trace of X is 1 and X positive semi-definite. So the variable here is this matrix X. So in other words, the bound FR coincides with the smallest eigenvalue of this moment matrix MR of F. So analyzing this parameter FR is understanding how does the smallest eigenvalue of this matrix MR of F behaves. Of course, in general, this is not so easy because This is incorporating the orthonormal base and so on and so on. But there is one case when we can rely on the classical theory of orthogonal polynomials, and that's the univariate case. So in the univariate case, when k is -1, 1, we are going to see that we can relate the smallest eigenvalue of this corresponding moment matrix to the largest roots of the orthogonal polynomials. And that's why we can analyze the bound. So that's what we do next. We are going to analyze the bounds for the univariate case when k is the interval -1, 1, and the polynomial f is linear, so that's x, or quadratic, that's x squared plus a linear term. So we now are in the situation where k is just the interval and f of x is x, the linear case. And now, as I just said, we use the classical theory of orthogonal polynomials. If we take this, the base of orthogonal polynomial with respect to the measure mu, they satisfy the 3-term recurrence. And this moment matrix I just introduced before, in the special case when f of x is x, this is actually known as, sometimes it's called the Jacobi matrix. It's 3-diagonal. This follows from the 3 terms recurrence. And the eigenvalues are the roots of the next polynomial PR plus 1. So this is just shows how the matrix, the Jacobi matrix MR of X looks like. So it's 3-diagonal, and the entries here are coming from the coefficients coming up in the 3 terms recurrence. This is really a very classic theory of orthogonal polynomials. So the smaller from this, we immediately get that the bound FR is the smallest eigenvalue of this matrix, which is the smallest root of the polynomial PR plus 1. And now for many classical measures like the Jacobi measures, the behavior of the extremal roots is known, and it's exactly known to behave in 1 over R squared. So this is why we deduce that the bound FR minus F min behaves like 1 over R squared. And this is tight, this is upper bound and lower bound. So this gives the exact behavior. So this was for the case of f of x is x. But of course, we need to understand also quadratic polynomials. So here is a typical quadratic polynomials in one variable. So there are two cases: either the minimizer is on the boundary or it's not in the boundary. So if the minimizer is on the boundary, then actually f has a linear upper estimator, and then we are back to the previous case. Remember, we have seen that if f has a nice upper estimator, being able to analyze the error of the upper estimator implies also being able to analyze the error of f. So from what I've just seen, we know that the upper estimator has an error analysis in 1 over R squared, so the same for f. We're done. And here, this holds for any Jacobi measure. We don't have to restrict to the Chebyshev measure. So why we need to restrict to the Chebyshev measure will become clear in a second when we deal with the case when the minimizer is in the interior. So then we just go back to what we know, that the bound, the parameter FR is the smallest eigenvalue of the matrix MR of F. And this matrix MR of F now looks like this. It's 5 diagonal and it's almost tuplets. And we would need to be able to understand what is the smallest eigenvalue. How does it behave? It's not so easy, apparently, but actually there is, we can make a trick. And what we can do is observe that if you forget the first 2 rows and columns, then you get a nice tuplets matrix here. This lower part here is nicely tuplets. Huh? There's all A's on the diagonals and all B's and all C's, and etc., where the A, B, C are given here. And this is what we exploit to do the analysis. So what we do is we get rid of the first 2 rows and columns because they are difficult, and what we do is we embed the lower part B, which is nicely 5 diagonal tuplets. We embed it into a circulant symmetric matrix by suitably define the first 2 rows and columns. And now by interlacing, then we know that the smallest eigenvalue of our original matrix is at most the smallest eigenvalue of B. which is at most the third smallest eigenvalue of C. But now C is circulant and symmetric, so we can exactly compute the eigenvalues and conclude. So we can conclude that this eigenvalue of C behaves like we want. And as a consequence, we obtain the analysis for a quadratic polynomial, and thus for any polynomial on the interval, and by looking at the product measures. So for the Chebyshev on the hypercube of any dimension and any polynomial, we get the analysis in 1 over r squared for the upper bounds. So we have the analysis of 1 over r squares for the hypercube for the Chebyshev measure only. And it will be necessary to be able to understand also how it behaves, for instance, for the Lebesgue measure or for other measures, if we want to transport this result to other sets, more complicated, like the ball or other sets. And this is what I will do next. But let me maybe mention briefly how we can already now lift what we learned to analyze the sphere. So we want to understand how the upper bounds behave when we minimize a polynomial f over the unit sphere. So we use again this trick which I mentioned, that we replace f by its quadratic upper estimator. But if we are on the sphere, then the quadratic upper estimator becomes actually linear. So that's nice, because now we have a linear upper estimator. So it's enough to analyze this linear upper estimator. And up to a rotation, we can actually imagine that this upper estimator is actually just a coordinate variable x1. So f of x is x1. It's enough to analyze f of x is x1. And now that's nice, because minimizing x1 over the sphere, we are going to be able to go back to the analysis of minimizing x1 on the interval. So let h of x1 be the univariate optimal density for this univariate problem over the interval, univariate, equipped with this measure. And because it's univariate and it's a linear minimize, so we are able to analyze this measure. I just explained this, then we use what we do. We have this univariate optimal sum of square density. We use it to get a good sum of square density for the multivariate problem, and combined with an integration trick. So I just take this h of x1, which is univariate. I take it as a multivariate sum of squares. And the fact that I've put here this weight function on the interval by the integration trick, I get that this is the same thing as the integral of h with respect to the Haar measure. Here mu is a Haar measure on the sphere. So it's just an integration trick. And I conclude by using what we had learned about the behavior of the bound for the interval. So of course, I don't expect that all the details are very immediate to follow here, but the point is that I wanted to explain how from the analysis of what we knew on the interval, we can lift the result to the unit sphere using this trick of integration. And okay, so I just wanted to mention that actually the bound is tight. So 1 over r squared is tight. One can show that for some polynomials, one cannot do better. So the bound is tight. And this relies on a link to Kubacher rules. But maybe let's not go into these details. So if we want to go to other sets like the ball or the box equipped with other measures, or the simplex or round convex bodies, we need to use other tricks. Let me introduce one such trick, which we call local similarity. And the idea is that we know the behavior of the bounds for a pair k hat, w hat. So here I mean that I have a measure on k hat, which is a Lebesgue measure with a weight function, w hat. So w hat is a weight function. So suppose we know how the bounds behave for this pair, and I'm going to give you a number of conditions, which implies that if these conditions are satisfied, then we can lift the behavior of the bounds for this pair to the red pair KW, which we didn't know. So what do these conditions say? So we have a polynomial f we want to minimize, and let A be a global minimizer. So we assume that our red set K is contained in the blue set K hat. So on K, I have a weight function W, and on K hat, I have a weight function W hat. And here are the conditions which we want. First condition is that the two sets should look the same around the minimizer, which means that there is a small ball which has the same intersection with K and with K hat. So this is a case here, or this is a case here. So the two sets look the same around the minimizer. The second condition is about the weight function. So they should look the same around the minimizer, which means so W should be at least a constant times W hat at a small ball around the minimizer. And the last condition is that the W should be at most W hat. We could also put here a capital M constant times W hat, but let's just keep it like this. And then if these three conditions hold, so if the two sets look the same and around the minimizer, and the two weight function also satisfy some nice comparability conditions around the minimizer, then one can see that F has an upper estimator G on K hat, which is exact, which means that both have the same minimum, F on K for F or on K hat for G, and having the property that the error of F on the pair KW is upper bounded by the error of G on the pair K hat W hat. So if we are able to understand this error, then we immediately can conclude something for this error on the red pair KW. And this kind of recipe, local similarity recipe, this is what we use to lift the results we had on the interval and to other sets. And here is a note that this first condition actually, of course, hold clearly. They are redundant if the minimizer happen to lie in the interior of the set. So the discussion will be mostly when the minimizer lies on the boundary of the set K. So I just here indicate very roughly how we are going to lift the result, the quadratic rate, which we knew for the interval, equipped with a Chebyshev measure to other sets and other measures. So first, we lift it to an arbitrary measure with a lambda at least minus 1.5 by applying this list of these similarity tricks, which I just mentioned. All the conditions are satisfied. And then by taking products, we get it also for the for the n-dimensional hypercube. Second, if we have a set K equipped with the Lebesgue measure, W is 1 means I take the Lebesgue measure simply. And when the minimizer is in the interior, then I will get the analysis for free because I have a compact set. I can always put it in a big box equipped with the Lebesgue measure. So then the conditions of the measures are clearly satisfied because we take both the same measure on both sets, and the similarity measure between the two sets around the minimizer is also clear because A lies in the interior. As another example where we can apply this technique is for when K is a standard simplex. So the only equipped with the Lebesgue measure. We only need to worry about the case when the minimizer is on the boundary. So if the minimizer is on the boundary, what we do is we transform our simplex into such a nice simplex here, which we then see as a subset of the hypercube. And if we suitably rotate, then our minimizer will be on this side of the simplex or this side. And then we have the local similarity. The simplex, the blue simplex will look locally similar to the big red hypercube. So we can apply the similarity tricks and transport the analysis for the cube to the simplex. So this tool doesn't apply if we would have another polyhedron which is not the standard simplex, because another polyhedron, for instance, would be if the minimizer would be at a vertex, and the vertex doesn't look the same on an arbitrary polyhedron and on the cube. So it's not, we cannot apply this trick for an arbitrary polyhedron polytope. And finally, for balls, again, we apply the same kind of tricks, combining with integration for the ball, and also for round convex bodies. So round convex body means that at every point on the boundary, there is an inscribed ball and a circumscribed ball, which are tangent to the convex body at that point. And these conditions are precisely what enables us to use this local similarity trick and to get the convergence analysis for round, so-called round convex bodies. So these are also the convex bodies which have a C2 boundary and are strictly convex. Okay, so for this whole list of sets, we have this analysis in 1/r², and this is best possible. So for most of these sets, there are examples which show that the analysis is tight. So if we want to go to more general convex bodies, so if we want to allow having a non-smooth boundary, or if we want to go to compact semi-algebraic sets, we need to do something else. So, and this is what I want now to describe, how to tackle the analysis for very general convex bodies or very general compact semi-algebraic sets. So I lost a bit track in time. How much time do I have? 10 minutes or?
Yes, 10 minutes. 10
okay,
minutes.
Very good. Okay, so as I briefly mentioned in the very beginning, so we are going to combine two ideas. The first idea will be to, in some sense, go back to the univariate setting, and we will do this using push-forward measures. And that's an idea which was introduced by Lasserre. And the second idea will be to use needle polynomials to construct good approximations of Dirac measures. So let me first describe the first idea, how to go back to the univariate case using push-forward measures. So first, let me just recall what is a push-forward measure. So remember, mu was this blue measure, was our reference measure, which we fix on the set K, and which we would like to analyze. Then mu f is a push-forward of mu by f, is going to be a univariate measure supported on the image of the set K under F, so the interval F min, F max. And by definition, if we integrate a function phi with respect to the push forward, that's the same thing as integrating phi over evaluated at f of x with respect to the blue measure mu. That's the definition of the push forward. And so motivated by this, we can define weaker univariate upper bounds. So I use a symbol FR and I put a subscript push forward measure, PFM, push forward measure. So this is this minimization program where the only difference, before we had here, I had this h of x here, where h was assumed to be arbitrary sum of square polynomial. And what we now do is we search for a univariate sum of squares S, which we evaluate at f of x. And this gives us this push forward measure bound, FR. So, once again, instead of having an arbitrary H multivariate sum of square, we restrict the search to a univariate sum of square S, which we evaluate at the polynomial f of x. So if we want, we can rephrase this in terms of using the push forward measure definition. It's the same thing as integrating T, S of T with respect to the push forward. And S is a univariate sum of square of the degree at most 2R, which gives a probability measure on f of k with respect to the push forward measure. So by construction, the push forward measure gives a weaker bound. If f has degree d, it gives its upper bound the bound, I mean the original bound of degree RD. So it's weaker. And these bounds still are weaker, but they still converge to the minimum of f. So this was Lasserre introduced these bounds and shown that they converge. And what we did together with Lucas, we showed that actually for these weaker bounds, we can show this error analysis. So this log r over r square. So you can actually analyze the weaker bound. So if this analysis, error analysis holds for the weaker bound, it also holds for the stronger bound, the original upper bounds. So how to do this? If you remember, I argued that if we look at this definition of the bound, this is a univariate. This is a univariate bound where we select the polynomial, the measure mu f as reference measure. So by what I argued a few slides ago, by definition, this push forward measure is nothing but the smallest root of the orthogonal polynomial of degree r plus 1 with respect to the push forward measure. But we are not helped with this observation because the push forward measure in general is not known. So we don't know what are the orthogonal polynomials, and we thus don't know how the extremal roots behave. So this is nice to observe, but we cannot use this in order to gain information on the behavior of the smaller roots. So we will need another approach to analyze this. And that's where we go back actually to the definitions of, to this idea that this optimal sum of squares that we are looking for, it should look like the Dirac delta at the minimizer. We go back to this idea and we try to construct a nice SOS approximation of the Dirac delta. And for this, this is very well studied in the literature in approximation theory. We use the needle polynomials of Crow and Svetitz, the so-called half needle. We don't need to go over the details. They are just defined in terms of Chebyshev polynomials. And let me just show. So the picture is a bit busy, but we should, my apologies for that, but we should just look at a green polynomial here, which is a half needle, which we show. So we are going to optimize, I didn't say it, but we may assume without loss of generality that f of k is the interval 0, 1. So the minimizer is attained at 0. So this is why we need a half needle which approximates the Dirac at 0. And this is this gain polynomial which we are going to use. So using this half needle, we are able to show this error analysis in log r over square for the weaker push forward bound. So this holds, so I have here written that this holds when K is a convex body, or when K is compact, fat, and semi-algebraic. Fat means having a dense interior. Actually, this holds in a more general setting. It's a technical condition which asks something about the behavior of the boundary. But this technical condition is satisfied, for instance, for convex bodies and for compact, fat, semi-algebraic set. So the analysis is almost tight in the sense that, and so it's almost tight. And on top of that, there can be a separation between the push forward bound and the usual upper bounds. So for the polynomial x to the k and the interval, actually we can analyze everything. The push forward measure, we know it's exactly 1 over r square because we can understand in this very special case, we can understand what the push forward measure is. It's going to be a special Jacobi measure. So this is why we can understand the behavior of the push forward bound. And for the original upper bounds, we can actually show this sharper rate because in this case, there were a lot of derivatives which vanish at the minimizer. So it's a technical condition which makes it able to get a sharper upper bound. So this line is telling us two things. There is a difference between the original bound and the push forward measure in general. And a second thing is that 1 over r square is the best one can hope for the push forward bounds. So there is a gap between 1 over r square and this log r square, which is coming here. And probably this log r square is just an artifact of the analysis, but we don't know how to get rid of it. So how to get rid of this factor, we don't know. So in the last couple of minutes, I just want to conclude with a number of remarks. So this is my last slide, last two slides of concluding remarks. So I have introduced these upper bounds and the weaker push forward bounds. So the original FR involves a matrix, computing the smallest eigenvalue of a matrix of Z size and to the R. An advantage of the weaker bound is that it involves an eigenvalue of a much smaller matrix of size r plus 1 because we get back to the univariate case. So this is very nice, size reduction, but there is a but. And the but is that to compute the entries of this matrix here, we need to integrate powers of f. So this can be very computationally expensive. So this is a remark I wanted to make. I also wanted to make a remark to simulated annealing. In simulated annealing, what you would do is you would sample according to the Boltzmann distribution for a certain temperature T. That would be how you would get bounds using simulated annealing. And there is a link, and the link is the following, which is that if we take the Taylor expansion of this exponential here, which is coming out from here, it takes a function in t, e to the minus t divided by the temperature. You take the Taylor expansion and you truncate at degree r, which is roughly 1 over the temperature. Then this actually gives you a sum of square density function, which you can use to analyze the upper bounds and actually to analyze the push forward bounds. So actually, in the case of convex bodies, the behavior of the Boltzmann distribution has been analyzed by Kalai and Vempala, and they show an analysis in 1 over r for the bounds and the minimums obtained by using the Boltzmann distribution, by using simulated annealing. So the simulated annealing behave like 1 over r, while the measure-based push forward measure behaves like this. So there is a link, and the push forward bounds, using sums of square densities gives a much better bound, theoretically at least. This is what these results show. So it has an advantage to search for an optimal sum of square densities. This is in a nutshell what one can say. The analysis extends for rational function and to the general problem of moments. And maybe one last thing I should have said way earlier. So these upper bounds actually gives an upper bound on the minimum. And of course, you could argue that there is an easy way to get upper bounds. Is maybe if you are, for instance, on the hypercube, just optimize over all the grid points on the hypercube, say with denominator r. If you do this, then you get a bound which will again have the same quadratic behavior. But to get, if you optimizing over all the grid points with denominator r requires r to the n function evaluations compared to solving an SDP with metric size n to the r for the upper bounds, sum of square base upper bound. So here it's exponentially many function evaluation. In terms of the number of variables, while here it's polynomial in terms of the number of variables for fixed r. And the last thing, so going back to the lower bounds, so I started with saying that there is only one case, the unit sphere, where there is this nice analysis in 1 over r square for the lower bounds of Lasserre, Parillo by Fang and Fuzzy. And interestingly, actually, the analysis of the lower bounds uses in some way the analysis of the upper bounds and for related univariate problem. and combined with other techniques, namely the polynomial kernel method. So there is an intrinsic something going on with the upper and the lower bounds, and this is an additional motivation for understanding the behavior of the upper bounds. And very recently, together with Lucas, we could extend these techniques of the unit sphere to the case of the binary hypercube. And it's open and ongoing work, how to extend this to more general sets K. Yeah. And with this, I thank you for your attention, and I am ready to take questions if you have. And the slides will be posted, and there will be a number of references on the slides, so we don't need to look at them. So
thank you very much for the very nice and very clear talk. Yeah, are there any questions? So, I mean, this what you formulated as being an open question. This was also what I had in mind. So, I mean, when you speak about general sets, you speak about sets which are not anymore assumed to be compact, or like?
No. I just mean, like, for instance, how does the hierarchy of low bounds for the ball, optimizing a polynomial over the ball, or even over the hypercube? It should be one over, it's expected that it should be at least as good as the upper bounds, so 1 over r square, but it's just extremely difficult to, so what you now need to show is you need to construct a nice sum of square decomposition for your polynomial. So,
but compactness is essential for all the results you presented, or is there something which can be said?
You could also say, so I restrict to compact, but for instance, the upper bounds can also be defined for non-compact sets. Then you should pick a suitable reference measure. But it seems less attractive. We looked a little bit whether something could be said for the quality of the upper bound for non-compact set. It seems less interesting. So this is why we restrict ourselves to compact. And for the lower bounds, the convergence actually needs compactness. In general, you need compactness.
Thank you. Are there other questions?
I would have a question, maybe.
Yeah, Matthias?
A more speculative question one. So in interior point methods, we have self-concordant barrier functions, which are always used to represent convex compact sets, and they give usually a good barrier calculus. So I was just wondering, looking at your slides, is there somehow in the complexity analysis somewhere a connection to the theory of self-concordance with the densities you pick here? In particular, also with the connection of simulated annealing, because you have this exponential function, so it looks a bit related when I think about the Nesterov-Nemirovsky construction of the universal barrier. Maybe.
My first answer would be I wouldn't see any link. No. I don't think. I wouldn't see any link. No. But I might be wrong. Huh? But Etienne also, I mean, I'm not an expert on interior point methods, but Etienne is, and my colleague, Etienne de Klerk, so I think he would have thought about it if there was any link. So my bet would be that there are no direct apparent links.
Okay, thank you. So then I have another question. So what I like very much was this technique to translate the rate you had under just 4 conditions you formulated.
Yeah.
So does this apply only in the univariate case, or this is a general technique?
So this similarity trick, I mean,
yes.
This was multivariate.
Multivariate, okay.
This was multivariate, yes, because okay. Univariate, there is nothing much to say. I mean, just an interval. So this was
indeed. Yes.
This was
okay. Yes.
I can show again the pictures, but we had the picture of, for instance, you put a simplex inside a box.
Yeah, indeed. Okay. Yeah.
Yeah.
So this was translation from one type of set to the other type of set.
Yes, exactly.
Okay. Okay. Yes, very nice.
Because we understand better the hypercube. So then you place, for instance, the simplex nicely in a
Yes.
nice position within the
Okay.
hypercube,
I see.
for instance.
Okay.
Yeah.
Yeah. So we have another question in the chat. MB. So please ask your question. Unmute your microphone and introduce yourself.
Okay, hello, thank you very much. My name is Matos Benko.
Oh, Martos.
Hello, thank you very much for your talk. I have, as I wrote, I have a bit silly question. Can we use such upper bounds to find a point, a feasible point, which is almost optimal? So, for instance, could I, if I'm interested in finding some approximate projection of a point onto set K, so the distance functions could be written as a polynomial, I guess. But do I also have basically the question is, do I also get some feasible point, which is almost optimal?
So that's a very good question. So there are cases where I can give you a yes answer. For instance, if you would minimize a convex polynomial, and if your set K is convex, then what you can do, so you have your optimal sum of square density, and then a way to get a point which is at least as good as a bound would be you just take the expected values of the coordinates. And this would give you a point which is in the set, and whose f value will be at least as good as a bound.
Okay, thank you very much.
So that's situations where we can do that. And otherwise, so in one of our papers together with Etienne, I mean, there are some methods how to sample. So the question you are facing is that you have dense, you have a probability distribution given by your sum of squares, and you want to sample using this.
Okay.
We did this, for instance, we implemented, for instance, for the box. But
Thank
this is something we are trying to think about more at the moment, yes. Because indeed, you don't only want to have the value, you would like to have a point, because if you get a good point, maybe you could combine with the first order method.
Okay.
The idea would be that you get a point which maybe is not yet the optimum, but hopefully it's in the, if life is nice, then this point would be in the good basin of an optimal minimizer. And of a global minimizer, and then coupling with the first order methods, and you could get to it. So this is something we would like to investigate in future. This.
Thank you very much.
Thank you. Are there other questions? Yes, Bruno.
Thank you very much for the talk. Actually, my question is somewhat related to the previous question. So these bounds, they talk about the difference between the values of the in a sense the relaxations in the original value. So even if I do not want to get an almost optimal point to the original problem, can I use these techniques to estimate the distance to the optimal set of so for example, suppose that you solve these relaxations and you get an optimal solution, and you do this at every degree. Can you say something about how these optimal solutions approach or if they actually approach the optimal set for the
But here I fix an objective function. So when you mean approaching the optimal set, or you mean for this, you fix an f.
Yeah, you fix f, and then you have a sequence of relaxed problems, right?
Yes.
So the results you talked about were about the difference between the optimal values, right?
Yes.
So I'm asking about the difference, about say the distance between the. Oh, of course, the optimal solutions wouldn't be unique, but you could say try to see what's the behavior of the optimal set. You know.
So then it would be the optimal set. We are optimizing over sum of squares. Huh?
Mm.
So then the optimal set would be the optimal sum of square density at every level. So you are saying how the optimal sum of square density behaves. So this is what I showed, for instance, I showed an example for the Motzkin polynomial, how the optimal sums of squares behave. But I guess this is not this optimum you want. You would like, so you see what I mean? The optimal set. The optimal, if you mean the set of optimizers of the relaxed problems, then the optimal set is a set of sums of squares. Well, it's a set of polynomials.
Okay. Okay, yes.
In your bound, you are optimizing over polynomials.
Okay, so that.
And then and then connecting to the previous questions, and what you would want is from this optimal sum of square density, you would like to get a nice point, a nice X close to the global minimizer.
I see.
Yeah, does it make sense?
Yes, it makes it. So I understood what I asked. Doesn't make a lot of sense. Okay, thanks.
Thank you.
Maybe I can stop sharing. Huh?
Are there other questions?
Oops.
So then I propose to stop here. So so you like to speak today. So it was a great talk. Thank you, Monique, for the nice talk.
Thank you.
And it was already announced. So we will post the video and the slides on our webpage. So yeah, I wish you all the best. So thank you very much. Thank you also to the audience for the questions and for the discussion we had. We just want to announce that the speaker next week will be Boris Mordokovic. So I wish you a nice week. See you next Monday.
Okay. Thanks a lot.
Thank you. Thank you. Thank you, Monique. Thank you. Bye-bye.
Bye.